In 2012, inside a machine buried 100 meters under the border of France and Switzerland, physicists isolated a single number, 125.25 billion electron volts. It was the mass of a particle called the Higgs boson, measured down to a fraction of a percent. That number sits inside the equations that decide why matter has weight, why atoms hold together, why a hand doesn't pass through a screen. According to those same equations, it also sits on the wrong side of a line nobody has managed to erase. Nobody built that line on purpose. It showed up in the math, and it hasn't gone away since. Before that line means anything, it helps to know how dangerous the universe already is without it. Interstellar space is not empty. It is soaked in radiation, littered with wandering planets kicked out of their solar systems before they finished forming, and threaded with dark matter that nobody has directly detected, but everybody can measure the gravity of. A supernova going off within about 26 light years of Earth would strip half the ozone layer and double the ultraviolet radiation reaching the ground. That specific kill radius comes around for any given patch of our galaxy roughly once every 600 million years. Rare, but not zero. Push the same explosion out to 326 light years, and the damage drops to something survivable. About 10% ozone loss, similar to what humans already did with aerosol chemicals in the 1980s. Gamma-ray bursts are worse. In 10 seconds, one can release more energy than the sun will produce across its entire 10 billion year life. Every gamma-ray burst ever recorded has come from another galaxy. If one ever fired directly at Earth from inside the Milky Way, it would burn through half the ozone layer before the 10 seconds were up, and the sky would need 5 years to recover. None of that requires new physics. It's simply what a universe this size, running for this long, eventually does to a small enough planet. The number pulled out of that Swiss tunnel is a different category of threat. It doesn't need a rare alignment, a nearby star, or a badly aimed beam of gamma rays. It only needs the universe to be exactly what its own equations already say it is. Every field in physics settles into a resting state, the arrangement it falls into when nothing is disturbing it. The Higgs field has one too, and that resting state is what gives particles their mass. What nobody has been able to close off is whether that resting state is the lowest possible one or just the nearest one. A bowling ball can sit in a shallow dip halfway down a hillside without being anywhere near the bottom of the hill. It isn't unstable exactly. Nudge it gently and it rolls right back into the dip. But give it one push past the lip of that dip, and it doesn't stop at the bottom of the nearest slope. It keeps going all the way down further than it started, and it never comes back. Run the Higgs field's numbers forward to the extreme energies of the early universe, using the measured masses of the Higgs boson and its heavier relative, the top quark. And the shallow dip we are sitting in stops looking like the floor of the valley. Somewhere out past 10 to the 10th billion electron volts, energies no particle accelerator on Earth will ever reach. A second, deeper valley opens up in the equations. The vacuum every atom in every star and every reader of this sentence is built on is not standing on solid ground. It is a shelf. A shelf can hold weight for a long time. Left completely alone, the odds of our vacuum spontaneously tunneling into that deeper valley work out to somewhere between 10 to the 400th and 10 to the 1000th years, a number so far past the current age of the universe that the word alone is carrying the entire sentence. The universe might not be alone. Microscopic black holes, if they exist at the right mass, warp the space immediately around them enough to act like a crack in that shelf. Instead of the whole flat expanse of vacuum needing to tunnel all at once, the collapse can start right at the crack and spread outward from there. Run the math on a black hole small enough, somewhere around 10 to 100 times the Planck mass, lighter than a raindrop, smaller than an atom, and the instant it finishes evaporating, a bubble of the deeper vacuum can nucleate exactly where it used to be. That bubble doesn't sit still. It expands outward at nearly the speed of light, rewriting everything it touches into a version of physics where the Higgs field sits at its new, deeper value. Particle masses reset inside the wall. Protons and electrons stop being able to exist in their current form. Every atom the bubble reaches comes apart at the level of its subatomic structure, converted into something with no stable chemistry left in it. There is no warning shot because there can't be one. The bubble wall moves at the same speed as the light that would carry news of its approach, so the two arrive together. Whatever is standing in its path experiences the end of atomic matter, and the first evidence that anything happened as a single event, with nothing in between. Nobody has observed this anywhere in the visible universe. That means either the small black holes required to trigger it simply don't exist in the right mass range, or some undiscovered particle beyond the ones already cataloged is quietly stabilizing the vacuum before it ever gets the chance to fall. Both possibilities are still live. Neither has been ruled out. That is the complication sitting under everything that follows. The thing standing between us and a silent, instantaneous erasure of matter is not a law of physics guaranteeing our safety. It is an absence of evidence for one specific, undiscovered kind of black hole. If the vacuum holds, that still doesn't mean the universe is safe. It means the next danger comes from somewhere else. Not from underneath space, but from what's making space grow in the first place. Since the late 1990s, astronomers have known the universe's expansion is speeding up, and they've pinned the cause on something called dark energy. In the simplest version of the model, dark energy behaves like a constant. As space expands, its density per cubic meter never changes, and it never gets strong enough to tear anything apart. Galaxies drift further from each other. Stars, planets, and atoms stay exactly as bound together as they've always been. Recent measurements from telescopes and surveys mapping the distribution of galaxies allow for a small deviation from that constant value. A version of dark energy that doesn't just stay the same strength as space expands, but grows stronger. Physicists call this the phantom regime, and if it's real, then dark energy density and the expansion rate of the universe both increase without limit, reaching an infinite value at a specific moment in the future. That moment has a name, the Big Rip. Right now, the distance between the Earth and the Moon grows by about 3.8 centimeters a year. A number tracked directly by lasers bounced off mirrors astronauts left on the lunar surface. That stretching today is caused by gravity dissipating tidal energy, not dark energy. The two forces are unrelated at that scale. But it's a useful yardstick for what space expanding physically means, a real, measured distance, quietly getting larger every single year. Whether anyone is watching or not, under phantom dark energy, that kind of stretching doesn't stay confined to safely negligible distances. It accelerates, and eventually it stops respecting gravity, electromagnetism, or the strong nuclear force. The very forces that hold your body, this planet, and every atom in it together. The sequence, if it happens, runs like this. Roughly 200 million years before the end, galaxy clusters lose their grip on each other and drift apart. About 60 million years out, individual galaxies come apart, their stars no longer close enough for gravity to bind the disk together. 3 months before the end, planets break loose from the stars they orbit. 28 minutes before the end, the stars themselves are torn apart by tidal forces stronger than their own gravity. 16 minutes before the end, Earth is ripped apart. A tiny fraction of a second before the end, less than a billionth of a second, the electromagnetic force loses the tug-of-war holding atoms together, and every atom in what's left of the universe dissociates into loose particles. At zero, space itself stops having a coherent geometry based on the current best estimates of that phantom parameter. The earliest this could happen is somewhere on the order of tens of billions of years from now, with plenty of models pushing the number out past 100 billion. It is not a Tuesday afternoon risk, but it is a mathematically real one, sitting in the same class of danger as vacuum decay. Not a monster from outside physics, but physics itself, taken to its logical endpoint. There's a third ending that doesn't require anything to tear or collapse. It requires nothing to happen at all, for long enough. This is the version most cosmologists currently consider the most likely. Not a bang, not a rip, but a fade. Two astrophysicists, Fred Adams and Gregory Laughlin, mapped out what that fade looks like by dividing the universe's future into eras, measured not in years but in powers of 10. Because by this point, ordinary numbers stop being useful. We're currently living in what they call the stelliferous era, the age when stars are actively forming and burning hydrogen. That era doesn't last forever. Once the last reserves of star-forming gas are used up, no new stars ignite, and the universe moves into the degenerate era. A stretch of time so long that white dwarfs, the slowly cooling embers of dead stars, have enough time to fully cool into cold, dark spheres called black dwarfs. If protons themselves eventually decay, which some theories predict but nobody has directly confirmed, even those cold embers dissolve, leaving black holes as the last structures with any mass at all. Black holes don't last forever either. Stephen Hawking showed they slowly leak energy as radiation and eventually evaporate completely, a process so slow for the largest black hole that it would take far longer than every other era of the universe's history combined. Once the last black hole evaporates, what's left is the dark era. No stars, no light, no chemistry, no structure above the level of scattered, isolated particles drifting through a universe that has run out of anything left to happen to it. That's heat death. Not an explosion, not a rip. A universe that simply runs out of differences. No hot next to cold, no full next to empty. And without a difference to level out, nothing can happen anymore. Every scenario so far assumes the universe keeps expanding forever. It might not if the deceleration of expansion ever won out over dark energy's push, a possibility current data makes increasingly unlikely, but not mathematically impossible. Gravity would start pulling everything back together. Galaxies would stop retreating and start approaching. Temperatures would climb as matter compressed into a smaller and smaller volume, ending in a big crunch. The mirror image of the Big Bang, everything driven back into a single impossibly dense point. Under ordinary general relativity, that point is a singularity, a place where the equations simply stop working. But two newer frameworks suggest the collapse doesn't have to end there. One, called loop quantum cosmology, treats space itself as built from discrete, indivisible units at the smallest possible scale, and shows that as density approaches that scale, a repulsive quantum effect kicks in and halts the collapse before it reaches zero volume. The other, built on a version of gravity called Einstein-Cartan theory, gets a similar result from a completely different mechanism. The intrinsic spin of every particle in the collapsing matter generates a repulsive pressure at extreme densities, again stopping the crunch just short of a true singularity. In both versions, the collapse doesn't end in nothing. It bounces and a new expansion begins. A new Big Bang, on the other side of the crunch. That raises an obvious question. If our universe can bounce into a new one, could this already be a repeat? Could there have been an earlier universe, and one before that, stretching back forever? The math says no, and for a specific reason. If each cycle generates a small amount of unrecoverable entropy, a basic result of thermodynamics that's difficult to avoid, that entropy has to carry over into the next cycle, which means each bounce should produce a slightly bigger, slightly longer-lived universe than the one before it. Traced backward, that same logic means each prior cycle would have to be smaller and shorter than the last, all the way down to a first bounce that had nowhere smaller to come from. An infinite chain of past cycles turns out to be mathematically incompatible with a universe that grows from cycle to cycle. Somewhere there was a beginning, so even the most cyclical version of the universe's fate still traces back to a single starting point. What it doesn't answer is a much stranger question that's been sitting underneath modern physics for 2 decades. Whether any of this, the vacuum, the expansion, the bounce, is physically fundamental at all, or whether it's a description running on top of something else entirely. There's a real number that makes this question harder to dismiss than it sounds. Physicist Jacob Bekenstein proved that the maximum amount of information a region of space can contain doesn't scale with its volume. It scales with the area of its surface. A 3-dimensional region can never hold more information than could fit on its 2-dimensional boundary, encoded at roughly 1 bit per patch of space the size of the smallest unit physics allows. That result, confirmed independently through black hole thermodynamics, is called the holographic principle, and it means the universe behaves mathematically like a projection. The deep structure of reality living on a boundary, with the 3-dimensional world we experience emerging from it. That's the physics that gives the simulation hypothesis its more serious backers. Philosopher Nick Bostrom framed it as a trilemma. Either almost every civilization capable of running a universe-scale simulation goes extinct before building one, or every civilization capable of it chooses not to, or we are almost certainly inside one right now, because simulated minds would vastly outnumber the original biological kind once the technology exists at all. Physicist Franco Vazza actually ran the numbers on what that technology would cost. Simulating a single gram of matter down to the quantum level requires more memory than there are atoms in the observable universe, because the number of quantum states needed doubles with every additional particle you track. Applying Landauer's principle, the physical minimum energy cost of processing 1 bit of information to a full, continuous, atom-by-atom simulation of something as small as Earth would demand more power than our entire galaxy produces. A brute force simulation of everything, all the time, at full resolution is not just difficult. Under the physics we currently understand, it is impossible, even for a civilization with unimaginable resources. That doesn't kill the hypothesis. It just means that if reality is simulated, it isn't running as a flat, always-on rendering of every atom in the universe. It would have to be doing something closer to a video game engine that only renders the room the player is standing in, computing detail on demand, exactly at the moment something interacts with it, and staying vague everywhere nobody is looking, which happens to be a rough description of how quantum mechanics already behaves. Particles without definite positions until something measures them, none of this is proof. It's a set of constraints on what a simulation would have to look like if one existed, built from real thermodynamic limits rather than science fiction. And if it is true, the unsettling part isn't the illusion. It's the off switch sitting outside a system that has no way to detect it coming. If there's an audience out there capable of building or watching something like that, it raises the question of why, across a galaxy holding somewhere around 100 billion stars, we haven't heard from a single one of them. That gap has a name too, the Fermi paradox. the statistics say advanced civilizations should be common. The sky says otherwise. No signals, no probes, no unambiguous evidence of anyone. One of the more logically consistent explanations, popularized by novelist Liu Cixin and built out of game theory rather than storytelling, treats the entire galaxy as a dark forest. The logic runs on two assumptions. Every civilization's first priority is its own survival. And the total resources in the universe are finite, which makes any two civilizations, whether they know it or not, competitors. Add one more constraint. The speed of light is too slow to let any two civilizations communicate fast enough to build real trust, and a chilling strategy becomes the rational one. Every civilization has an incentive to stay silent, because it can never be sure a civilization it reveals itself to is friendly, and it can never prove its own intentions either. If contact is made, and the other side turns out to be hostile, or simply more advanced, the slower civilization doesn't get a second chance. Under those conditions, silence isn't caution. It's the only stable strategy that doesn't sometimes end in extinction. It's a compelling argument, and it has real critics. Any civilization advanced enough to threaten others is also, by the laws of thermodynamics, forced to leak waste heat as infrared radiation, something modern telescopes are built to detect at interstellar distances. Total concealment might not be physically achievable at all. And there's a second, sharper problem with the theory. Humanity has been leaking radio and television signals into space, unshielded, for about a century now. If the galaxy really is a dark forest where discovery means annihilation, that century of noise should already have been enough to bring something down on us. It hasn't, which either means intelligent neighbors are far rarer than the statistics suggest, or the dark forest isn't quite as absolute as the theory claims. Whichever is true, the fact that Earth is still here after a century of broadcasting either says something reassuring about how empty the galaxy is, or something we haven't figured out yet about why the silence hasn't been broken. There's one more version of not real worth sitting with, and this one doesn't involve simulations, aliens, or anything outside physics at all. It comes from thermodynamics, and it points directly at the reader. In a universe old enough and large enough, particles jostling around in a low-energy state will, purely by random chance, occasionally arrange themselves into complex ordered structures, the same way a shuffled deck of cards will, if shuffled enough times over enough trials, eventually land in perfect order by pure accident. Given enough time, those random fluctuations can, in principle, assemble something as complex as a functioning, conscious brain, complete with a full set of false memories. A childhood, a family, a decade of Tuesdays, and the specific memory of reading the words that came before this sentence. Physicists call this a Boltzmann brain. And the disturbing part isn't that it's possible. It's the math around how often it would happen compared to how often a brain like yours would form the ordinary way, through billions of years of stellar and biological evolution inside a genuinely low-entropy universe. In a universe that keeps expanding forever, the number of these randomly assembled brains grows without limit over time, while the number of brains produced the ordinary way is fixed, capped by the short window when stars still exist to make it possible. Run that comparison out to infinity, and the random brains outnumber the real ones by an unbounded margin. Statistically, on that basis alone, a typical conscious observer in an eternal universe is far more likely to be a fluctuation than a survivor of 13 billion years of cosmic history. The reason this hasn't been treated as a serious threat to your sense of reality is that it makes a testable prediction, and the prediction fails immediately. A Boltzmann brain's memories would be far more likely to be simple and short than to contain a coherent, structured decade of consistent experience, because simple, false memories are statistically cheaper to randomly assemble than complicated, self-consistent ones. The fact that the world keeps behaving in an orderly, predictable way from one second to the next, rather than dissolving into chaos the instant after it's observed, is itself evidence against being one. Physicists, including Sean Carroll, have proposed that if the vacuum itself is unstable in the way Chapter 1 described, it would decay long before enough time passed for these brains to statistically dominate, which cuts the problem off before it becomes a real prediction about anyone's mind. Others argue that in a truly static, unchanging vacuum, nothing actually fluctuates at all. The appearance of random events popping into being is a mathematical artifact of how physicists were doing the calculation, not something physically happening in empty space. Either way, the fact that this took real physicists' real careers to work out, rather than being an obvious mistake, says something about how strange this particular corner of cosmology gets once entropy and infinity are put in the same sentence. There's a final layer to this, and it comes from an odd coincidence buried in a basic equation. Every black hole has an event horizon, a boundary defined by its mass through a formula that's been in textbooks for over a century. Run that same formula on the total mass of everything inside our observable universe, and the radius you get back is close enough to the actual radius of the observable universe that it's difficult to dismiss as a coincidence. Some physicists have taken that seriously enough to propose that our universe isn't just similar to the inside of a black hole. It might literally be one, the interior of a black hole that formed inside some larger parent universe we have no way of observing from in here. If gravitational collapse doesn't end in a singularity, the way the newer bounce theories suggest, then every black hole forming right now, in every galaxy, could be a doorway. Matter collapsing past the point where our physics can follow it, and re-expanding on the other side as the beginning of an entirely new, causally disconnected universe. Physicist Lee Smolin pushed this idea one step further, into something closer to evolution than physics. If the physical constants of a daughter universe come out slightly different from its parents, purely by chance, during the bounce, then universes that happen to produce more black holes will produce more offspring. Run that process over enough generations, and the multiverse ends up dominated by universes tuned, almost like a species, to be good at making black holes, which happens to require conditions not far from the ones that also make stars, chemistry, and planets possible. Under that framework, the fine-tuned, life-permitting universe we live in wouldn't need a designer or a miracle to explain it. It would be the expected outcome of countless generations of cosmic natural selection, and every black hole visible from Earth tonight would be, from a certain angle, a nursery. None of these 8 ideas carry equal scientific weight, and treating them as equally likely would be dishonest. Ranked by how seriously working physicists currently take them, heat death sits at the top. It requires no new physics, only the standard model of an eternally expanding universe running its course. False vacuum decay comes next, resting on measured particle masses that genuinely do point toward a metastable vacuum, even though the black holes needed to trigger it have never been observed. The Big Rip follows, permitted by current data but not required by it. The Big Bounce sits in the middle, grounded in real quantum gravity research but still short of any observational confirmation. Below that, the Boltzmann brain problem functions less as a prediction and more as a stress test for cosmological theories, a scenario nobody expects to literally happen to them. The simulation hypothesis and the dark forest sit lower still, coherent, internally consistent, but resting on assumptions about computation and alien sociology that nobody has been able to test. Black Hole Cosmology sits at the bottom of the list, elegant, mathematically suggestive, and still essentially unprovable with instruments that exist today. What connects all 8 is the same thing that number from that tunnel under the Swiss border pointed at from the very first sentence. 125.25 billion electron volts isn't just the mass of one particle. It's the number that currently decides whether the shelf we're all standing on holds or falls. Every other theory in this ranking assumes that shelf survives long enough for something else. Expansion, entropy, collapse, computation, silence, chance, or a nested black hole to become the thing that finally gets us instead. The universe isn't dangerous because of monsters. It's dangerous because the equations that describe it, the same ones that explain why atoms exist and stars burn, and this sentence can be read at all, contain the mechanisms for their own ending. Built into the structure from the start, that number measured under Switzerland in 2012 hasn't changed since anyone wrote it down. What's still unresolved is which side of it we're actually on, and whether physics will finish answering that question before the answer finishes with us.